Jordan Pollack, and I'm a professor at Brandeis University, which is just outside of Boston. My work has been across different parts of the field in natural language and neural networks and dynamical systems and fractals. And most of my work for the last 25 years or so has been in evolution. I would say that mindless intelligence is a position I took to consider the 50-year anniversary of AI and what's been achieved. And my feeling is that there's a lot of intelligence in nature, in evolution, in development, morphogenesis, in immunology, in the immune system, in the development from fertilized egg to the fetus, in the support of ecosystems, keeping the conditions right for life. All over nature are these quite large and quite impressive intelligent structures that have evolved, that have emerged, that have taken advantage of physics, and that the focusing of AI on human-style intelligence or on human-style intelligence that's the result of introspection is a mistake, because we know from a lot of the research on consciousness and on human problem solving that we don't think the way we think. So saying, here's how I play a game, here's how I play backgammon, and now write a program that plays the way I think I play, and that could lose completely to another version of backgammon, which is a purely numerical solution. So mindless intelligence is my way of saying that instead of focusing on human genius and what humans have that animals don't, we would make more progress by looking at how intelligence arises in nature and try to figure out the principles and the mathematical principles underlying those forms of intelligences, and how do we exploit those forms of intelligence for the kinds of tests that have value. There's several fields. The field of coevolution in machine learning is supposed to capture the idea of an arms race, which you can get from sexual selection, like the peacock's tail, or contingent development between species. The idea of machine learning is that a coevolution could lead to an arms race, which would lead to increasing complexity without end. Now, that hasn't happened, despite a lot of people's efforts. Some people think it's run into a wall. I think that it hasn't run into a wall, but we have a deeper understanding now of the fact that most evolution that uses competition is governed not by where you want it to go, but by where it itself wants to go, which is into a Nash equilibrium. So Nash proved in '54 that any competitive game has these equilibria, and we set up our evolutionary algorithm as a game, and we don't realize it has these equilibria that it needs to go to. So we call it coevolution. There's a movement, a lot of friends of mine working on something called open-ended evolution, OEE. Deep evolution is a branding that I'm trying for evolution, which does not get stuck in equilibria, but continues to evolve for hundreds of thousands or millions of generations. And I only have a few cases where that works. And one is an old piece of work by Christian Lindgren in Prisoner's Dilemma. And the problem with deep evolution in Prisoner's Dilemma is that the best solution might be the smallest program tit for tat. So if you want deep evolution to give you complexity, you have to find a different task than Prisoner's Dilemma. So it's a rebranding of open-ended evolution, cognizant of the fact that there are a lot of equilibria phenomena that you need to finesse. You can't simply say, I don't believe in equilibria, because they come on their own. It is happening. It is slow. All of the forefathers of the field Newell, Simon, Minsky, and McCarthy have all passed away. It was very hard to be a leader in a field where the distinguished founders are still hanging around and giving interviews to the journalists. That's starting to change, but there's two more generations of leaders, who don't really want to give up the reins of power and the reins of what direction the field should go in. I think that what's interesting is that when there are successes, the overarching structure of the field wants to embrace those successes as successes of AI. But while the fields are in question, there's a sort of "you're not one of us" type of dynamic that goes on. So right now, AI is loving deep learning, even though 5 or 10 years ago, neural networks were not really being covered by the field. And now they are because, hey, it's a very successful part of AI. But that required a change of attitude. And in evolution, has not had the greatest set of wins. And so it's still seen as a little bit of ugly duckling phenomenon for the field. But it is changing because there are multiple societies, there are multiple journals. AI still has a hold on the overall field. And, just to give you an idea, the AAAI changed its name from the American Association for Artificial Intelligence. They changed their name to the Association for the Advancement of Artificial Intelligence without changing their acronym. So now it's Global Association. But it's still being run out of the same Palo Alto office as it's been running for 30 years, and the same executive staff that it's been run for 30 years with the same close ties to Stanford and MIT that it's had for 30 years. So democratization is there for graduate students. They can work on whatever area they want, wherever there are jobs. And so there's a lot of graduate students working on deep learning because there are lots of jobs there. But it's coming. Companies that have immense infrastructure that academic science doesn't have access to. Okay, and especially if you're determined that you want to do deep learning, and if that means that you need millions of GPUs to do it, you're not going to get it in the university. Might be able to get it in a company like Sentient. I don't know what their facility looks like, but basically some of the best PhDs now are going to work at Google and Facebook and Twitter and others, Microsoft, IBM. And that's ultimately bad for the science if you eat the seed corn and you don't have new professors coming into the field. So I think that's an issue, but I'm confident that there'll soon be in deep learning winter. It's like we've had AI winters in the past when expectations are raised so high that they have to be dashed, and then investors lose money and then they turn away. I think that a combination of a collapse in the value of deep learning stocks, combined with a collapse of Bitcoin, could trigger a winter. If IBM decides that it's spent enough money on Watson and decides to kill the project, okay, what impact would that have on medium-scale capitalized AI companies? So these things do tend to come around in cycles. And I've been through several. So I don't think that deep learning is sort of the end of, or even the beginning of the end of AI. I think it's just the coming of age of pattern recognition and applications of pattern recognition that we knew pattern recognition would have. And so it's very exciting and all, but it's like winning at Jeopardy or winning at Go or winning at backgammon. It doesn't necessarily transfer into general intelligent thought. And that's the big problem for AI, is the silo. Something works on one thing, the best chess player in the world, but it can't tie its own shoes. I worked with my students and postdocs on a field of I call Coevolutionary Robotics, and that was the idea that rather than having engineers build a robot and giving it to programmers to program the robot, that in nature there never is a body without a brain. So the idea I had was to use a coevolutionary arms race between a simple body and a simple brain and a more complex body and a more complex brain, basically climbing up the complexity ladder with interactive species of bodies and brains. And it didn't work out exactly the way I initially saw it, but we've had 5 or 6 generations. And every time we set up a simulation of a whole, really a language of different robot bodies and a concurrent language of robot brains, usually neural networks and recurrent networks of various sorts. Whenever we did the evolution, there would be the invention of certain kinds of structures that might have required an engineer. But it's the interaction of the physics engine with the evolution which does creation. So we saw in the first generation of Lego robots, we saw the emergence of cantilevers and triangles, and in the first generation of golem robots, we saw ratchets and breaststrokes and rolling and all sorts of different kinds of locomotion evolving. And it was seen before in Carl Sims's work in 1994, which was a tour de force that no one was able to replicate for 10 years. The code wasn't released, and it was custom, and it ran on a connection machine. There were various other reasons why Sim's work was not replicated, but he showed the construction of these artificial life, computer graphic creatures that moved in amazingly lifelike ways. So the interaction between the physics and the evolution is a form of invention. I call it the Sims effect. And a lot of people, like the intelligent design people, still won't admit that evolution is capable of designing structures that we've seen in natural life. But that would be said, the mechanisms that I saw, Carl Sims saw, had the order of 10 plus or minus moving parts. Whereas in real life, the eye or the wings flapping, whatever, has hundreds to thousands of moving parts. So again, it's sort of the same question as deep evolution is, how can we get something to run without reaching equilibrium early, such that complexity develops and develops over time? So when we do that, we'll have robots that are extremely complex, and then we'll face another problem of, well, how do we manufacture these robots? Well, I have an answer for that too, but it's a longer one.